In our last video, we took a look at how to use the principle of impulse and momentum when we're solving problems for rigid bodies. And just like we did for a particle, we can also have problems that use conservation of momentum for rigid bodies. And these are a lot of times problems where you have impact, right? Where you have two things that are colliding with each other. So anytime that you have something where there are no other external forces, only forces are within the system of two things interacting together, no external forces, that's when you can use this conservation of momentum. And so if we remember, our conservation of momentum is when the summation of all of our initial masses times initial velocities equal our final masses times final velocities. So that's our conservation for linear momentum. And then we also have our conservation of our angular momentum, which is when our angular momentums, the summation of all of those initial angular momentums, equals the summation of all those final angular momentums. And this is the one that we see more often applied in our rigid body problems. So our conservation of momentum is typically more often used with our angular momentum here, and we're going to take into account both the linear and angular momentum inside of these angular momentums. And what I mean by that is we're going to take into account those velocities with r times m times v inside of this angular momentum, as well as those rotational ig times omega, those angular velocities. So both linear velocity and angular velocity can be put into our relationship of our conservation of angular momentum here. And so these are typically pretty straightforward. The setup can be a little bit difficult sometimes. So we'll take a look at just one example of how to use this conservation of momentum when we have some kind of impact problem. So in this example, we have a 5 kilogram slender rod shown that's pinned at end O and is initially at rest. If a 4-gram bullet is fired into the rod with a velocity of 400 meters per second as shown, determine the angular velocity of the rod just after the bullet becomes embedded in it. Right, so this is one where we have a collision where the bullet is embedding itself, and then when it embeds itself, this rod is going to want to swing out in a rotation about that fixed axis, in a rotation about our point O up there. So what we've got going on is that before and after, right? This is a collision style problem, and we know with collisions, there are no external forces. It's only the forces of the bullet and the rod interacting with each other, no other external forces. So it makes it a good candidate for conservation of momentum. So what we're going to do first is the way that we approach every problem, just drawing out those diagrams. Draw out your free body diagram. And we're also going to draw out our before and afters, right? Drawing out the before and afters of our kinematic diagrams, kind of showing what are the velocities that are happening right before impact and then right after that impact. So we'll start with that free body diagram. We have the rod that has that pin connection up at the top. So we know that we have that OY and OX, those reaction forces from our pin there. They gave us in the problem statement, they said that it's a 5 kilogram slender rod, so we know that it has a weight to it. Acting in the center of this slender rod, the weight is going to be 5 kilograms times 9.81. And then if we think about what's happening with this system after impact, right? We're trying to find that angular velocity just after the bullet becomes embedded in it. So that's the diagram that I'm going to draw here for my free body diagram. So when that bullet becomes embedded, it's also contributing a force here of its own weight within the rod, right? It's adding weight to that rod. it's a very small weight. It's only 4 grams, but it is adding weight to this rod here. I'm going to say 0.04 kilograms times 9.81. So that way it'll give me in newtons what that weight is for the bullet that it's adding to this rod here. So that's our free body diagram, right? That's the bullet being embedded in it. It's not contributing any more force. All of it is now swinging. It has that momentum that is converted from that impact into the swing. It's no longer contributing a force in our X direction, though. Right? It's fully embedded at this point. But let's take a look at what this looks like for the before and after for the kinematics. Right, so this free body diagram is really only for the after. It's just the once that bullet is embedded, what forces are happening on this rod. But let's look at these kinematic diagrams. So if we look at the before, what we have before is we have our rod and we have our bullet, and they are separate entities. Right, where you have the bullet down here impacting into that rod. So right, like just that split second of time right before it hits, the only thing that has any momentum to it is going to be the bullet. And so it comes in with that velocity VB of 400 meters per second, as we have in the problem statement up there. So this is the mass of the bullet times VB1. That's the mass of the bullet times its initial velocity. That's the momentum that we have in the before. And then the rod's not moving in the before, right? The rod is just sitting there. So that's all we have. Those are the only velocities involved in our before. And if we look at the after, now what we have is that rod beginning to swing. Right, so we have an angular velocity about our point O up there. We have an angular velocity, IO times omega. Right, from that velocity, from that bullet getting embedded in that rod there. We also have our bullet with its own velocity. Right? So the mass of the bullet here times the velocity of the rod. Right? It's trying to move to the right. The instant that immediately after it strikes, the bullet is still moving to the right. But now it's inside of the rod. It is moving with the rod to the right, where the whole rod is also being sent mrod times VG. This whole thing, the instant it strikes, is immediately given a velocity to the right. Right? And then as it's given that velocity to the right, it's going to start swinging up in that angular velocity, in that counterclockwise motion about O. So it starts vertical. Right after impact, that rod has a velocity, the same velocity that the bullet has. It's trying to move to the right. It's in relation to that angular velocity about O there. So all of those have to be taken into consideration, right? Rod has a velocity, bullet has a velocity, the combination has an angular velocity. We did our free body diagram capturing all those forces, the kinematic diagrams kind of showing those before and afters. So again, there's no external forces here. It's a good candidate for our conservation of momentum, as we've discussed. And in this case, we're going to go with our conservation of angular momentum. Right? We have an angular velocity there. And in a lot of these problems, for our rigid bodies, we're going to want to use our angular momentum, conservation of angular momentum. We can use conservation of linear momentum if it makes sense to do so, but most of the time with these, it's going to be your conservation of angular momentum. So looking at our before diagram, we've got just the bullet. Right? The bullet is the only thing with any momentum whatsoever. So our initial momentum, our initial angular momentum, is going to be r, b. That's going to be our distance from where b is to where we're rotating about. rb, mb, vb1. Right, if we recall, one of our definitions of angular momentum is rmv. So this is what I'm using to relate our bullet's velocity to our angular momentum here for our initial angular momentum. Because it's the only thing. It's the only thing in this kinematic diagram. It's the only thing with velocity before impact. So this is what goes in our initial angular velocity, or our initial angular momentum, I should say, is rb times mb times vb1. Then we'll look at this this after diagram, right? This after diagram with these kinematics, or in our kinematic diagram, has all of our final values. So again, we're going to have that bullet having a velocity. RB, MB, VB2. But in this case, our VB2, the final velocity of the bullet, is just the final velocity of the whole thing. I'm actually going to rewrite this. I'm going to call this VG. This is the whole thing together. Velocity of the whole system right after impact. We've also got the rod. The rod has a different mass, a different radius, and so it needs to be accounted for in its own little segment here, even though it has the same velocity of the bullet, where we're going to have the radius from O to the center of our rod here, times the mass of the rod, times VG. So these VGs are the same. Everything's going to move with the same velocity since the bullet is inside of the rod now, but they do have different distances, different masses that have to be accounted for separately. And then finally, we have our IO omega. We have that angular velocity component where we had HO equals IO omega, so this just pops in here as IO omega, our moment of inertia about O times omega there. So looking at this, we're definitely going to need that IO. We're definitely going to need that moment of inertia. So let's go ahead and grab that. So our moment of inertia, we have a slender rod here, a slender rod rotating about its end. If we go look that up in the tables in the back of our book, that's 1/12 ml squared. So 1/12 ml squared. And I'm just going to start plugging numbers in here, see how far we get. So RB, again, that's our distance from O to B, where that bullet is striking, and that is 0.75, so I've got 0.75 times the mass of the bullet, 0.004, times the initial velocity of the bullet. But notice this needs to be the initial velocity only in our x direction, right? Everything else here is only in our x direction, so if I want to use the scalar form of this, I need only my x value of VB here. So my x value of VB is going to be 400 times cosine 30. 400 times cosine 30. That y component of the velocity isn't going anywhere in our conservation of our angular momentum. All right, so mass, so we had RBV, that's our left side of our equation, and then I'm going to start plugging things in the right side. Got RB, that's the distance to our bullet again is 0.75, mass of our bullet 0.004 times VG. We don't know what that VG is. They didn't give us a final velocity. We're trying to find that final angular velocity. Plus our rod stuff. So our rod stuff, our distance from O to to the center of the rod, since that's where our center of mass is going to be 0.5, since that rod is 1 meter long. So 0.5 times the mass of the rod, which was given to us, 5 kilograms. 5 kilograms times Vg plus our IO times omega. 1/12 times the mass. And our mass here, remember, this is just for the rod, so it's just that 5 kilograms times 1 squared times omega 2. Right, that final omega. You could leave it just as omega. Or say omega 2 to make sure you know it's final angular velocity. That's your call. So when we get to this point, we notice, oh man, I have two unknowns here. I've got Vg and omega. What am I going to do with that? How am I going to relate those things? How can I relate Vg and omega together? And if we think back to our kinematics, we think, oh, when we have rotation about a fixed axis, then I can use V equals omega times r, right? And so that's great. That really solves a lot of our problems here, where my Vg here attached to my bullet, I can say my Vg for my bullet there is going to be Vg is omega times r. Vg is going to be omega times 0.75. 0.75. That bullet is 0.75 away. For my other Vg, use a different color here. For my other Vg here, I can say, okay, this Vg for the rod is going to be 0.5 times omega, right? That r times omega. So now I can get everything in terms of the exact same omega, instead of trying to figure out what those velocities are for the bullet and for the rod there. And so when I do that substitution, I can come back in here and I can say, okay, perfect. This is now solvable. I put in 0.75 omega, 0.5 omega. I can put this into my calculator and solve for 0.62 radians per second. Right, so I had to go back and use those kinematic relationships that I'd found, way back when we were learning about the kinematics of this. Knowing that this is rotation about a fixed axis, we were able to relate those things together instead of trying to find these VGs independently, like trying to, solve them in another way or solve them with our principle of impulse and momentum, which we could. This problem is entirely solvable. You can still use principle of impulse and momentum with the 3 separate equations to find your omega, but this conservation of momentum is just another way to do that.